Okay, let's get started for today. Today we're going to talk about how you might think about choosing prior distributions, but a lot of the stuff that we talk about today is also applicable to choosing a conditional distribution for the data given the parameters, which then becomes your likelihood function. A couple of announcements. First, some of you are concerned about your grasp of probability, and that's understandable. There was a book on the syllabus called Introduction to Probability that I think is really good, but Columbia lost its online subscription to that book, so the link was not working. However, Columbia subsequently found the ebook that they have a license to, so I will upload a syllabus that has the new link to that book and some slightly changed readings in future weeks. So that has a lot of, it's a textbook, so it has a lot of exercises in the back that back of each chapter that you can practice with, and it corresponds to the cheat sheet for probability that someone posted on Piazza back the first week or so, which is really good, but you also need the book to go along with it in order to, understand where the things in the cheat sheet are coming from. This is also the textbook that corresponds to a series of video lectures that Joe Blitzstein, who wrote the book, recorded on his when he was teaching a probability class to undergrads based on that book. Anyway, those videos are on YouTube and iTunes, and so they're easier to follow along with if you have the book. So when he's referring to page numbers and stuff like that, you can flip to those. So that is a good resource for learning more about probability in a rigorous way that is applicable to both the frequentist approach and the Bayesian approach. Also, it came to my attention that Mathematica is offering students a license to Mathematica for free. I don't have the link memorized, but anyway, if you search like Mathematica Columbia, there's a link on the CUIT webpage that says how you can get a student license of Mathematica, which is occasionally useful for computing some integrals or something like that. Wolfram Alpha is usually good for that too, and it's online, but it only gives you like 10 seconds of computation time. And so if you're doing something that is a little bit harder, it can be nice to have the desktop untime constrained version of that. Okay, and I will be posting the second homework assignment tonight. It'll be due in a week and emphasize continuous probability distribution stuff. So I should say, as soon as I posted that Stan was seeking an additional $10 million, I got an email out of the blue from the RStudio people who are interested in funding Stan. It was only for 10,000 rather than 10 million, so we'd still have a little ways to go on that. Of course, even 10,000 would be like twice the legal limit for having to disclose it as a conflict of interest from one company that basically makes RStudio available for free, and people who make Stan also available for free. But in any event, somehow it still becomes a conflict of interest due to the fact that I work at Columbia and work outside of Columbia. So we got started to get some good questions on, or well, we've always had some good questions. We started to get good questions at a more rapid rate on Piazza. And one of them was about the difference between, or a couple of them really, about the difference between the Bayesian and the frequentist approach, which we've talked about a lot so far this semester. We'll continuing to talk about it a lot for the rest of the semester. But in order to really understand the difference at the technical level, you have to understand a little bit about probability, and you have to understand about these expectations. So Bayesians interested in a number of things, but ultimately interested in taking expectations of some g function of the parameters. So what is the expectation of g? G could be a utility function for taking an action that depends on this unknown state of the world that is ultimately a function of theta. And so analytically, this is usually impossible. We can approximate it with Monte Carlo draws. But anyway, we evaluate the g function, multiply by the posterior PDF for the unknown parameters theta, given the known observations on the outcome and the x's and stuff. There's n of those. And in order to evaluate this expectation analytically, we would need to do the integration over theta 1, theta 2, all the way up to theta k, where k is the last parameter in our model. And so that's really what we're going for. We have to, approximate it with Monte Carlo stuff, but conceptually, that's what we're after. Some function of interest, like a utility function, weighted by the posterior PDF for the unknowns given the known data values and integrated over the parameters. Of course, from a frequentist perspective, or Fisher's perspective at least, doesn't make any sense to integrate over parameters because parameters are these sort of constants like Planck's constant or Avogadro's number or something that you may not know if you're not a physicist, but it sort of has a known or a particular value that may not be known to you. And it doesn't make sense to think about, well, what if theta were this? What if theta were that? It's sort of like saying, what is the probability that E is less than 3? If you don't know what E is, that may kind of sound like a reasonable question. But if you think of theta as being like the transcendental number E or pi or something like that, it doesn't make sense to make probability statements about E. It is, equal to 2.71, etc. Definitely not 3. It's definitely less than 3. So there's no sense in making probability statements about something that is not a random variable. However, Bayesians are treating their beliefs about theta as a random variable, updating them given the in observations on y, and then taking the expectation of this function of interest over their beliefs about theta conditional on the data. And frequentists are ultimately interested in basically the exact opposite thing. They're interested in expectations of the functions g of the data, y1 through yn, where g might be some point estimator of theta. So for example, if this was just like trying to estimate the mean of y or something like that, you could just take y1 through yn, sum them up, add them, divide by n, and that's an estimator of the mean of y. Anyway, so they have some g function of interest, which is usually a point estimator of some parameter, and then they take their g function, multiply it by a conditional PDF for the data generating process, given the parameters, and they integrate that whole thing over the possible values for the data. So dy1, dy2, dyn. And so they are taking the expectation of some function of the data weighted by a PDF for the data given the unknown parameters and integrating it over the y's in order to take the expectation of their point estimator. And hopefully the expectation of that point estimator is equal to theta or close to theta or something like that. And so if you look at these two, you might say, well, they're both integrals. They both involve numbers and functions and stuff like that. And I think a lot of people who don't have a whole lot of experience with probability, or at least probability with continuous random variables, and seeing expectations defined in terms of integrals are like, well, they're both doing integrals, so it's, probably pretty much the same thing. But they are very different integrals. First one is integrating over the space of theta. Second one is integrating over the space of y. Moreover, the first one is using as its weighting distribution the posterior PDF of what you don't know given what you do know. The second one is using the weighting function, the PDF of the data, conditional on the unknown parameters. Moreover, the G functions of interest are different. First one, something like utility, where theta governs the states of the world. You're not exactly sure what those are. In the second case, some function of the data generating process. So these expectations of estimators that frequentists come up with are all pre-data. So this is what you would expect the estimator to be before you collect the data. Nothing really of the probability statements produced by frequentists are post-data. None of them is conditional on the n observations of data that you have. They're all conditional on these unknown parameters. And a lot can be said for or against either approach. I think it's hard to minimize the differences between people who take integrals like this and people who take integrals like that. But I think the simplest way to look at it is do you want to do a posterior PDF of what you don't know conditional on what you do know, or do you want to base your whole probability thing about PDFs that condition on theta, which you don't know? So in the Bayesian approach, we have the opportunity to condition on data, which we actually could have in our hands. And the frequentist approach is based on doing a whole lot of technically sound math on PDFs that condition, take as given stuff that is not actually given, but you're trying to estimate. And so it's a very counterintuitive way of going about estimating theta by conditioning on theta. Delete.
Maybe we should talk about what take as given is function form, or what
no, taking the parameter as given. So this is a conditional PDF. Now, of course, they don't have theta, but they derive these expectations and confidence intervals and so forth that are correct following from their assumptions, irrespective of what theta is. So they don't know theta. They're using conditional PDFs that condition on theta, but the math that they get out is sort of correct for all values of theta in the parameter space where theta could live. I mean, we'll go through an example in a second, but sort of, do you integrate over the parameters? Do you integrate over the data? Do you use a conditional PDF for theta given the data, or a conditional PDF for the data given theta? Do you evaluate a G function of the parameters or a G function of the data? And so to say, well, they're both integrals, I think is like very simplistic. All right. So this is what we put up at the end of class on Tuesday, how a Bayesian would generate data from the prior predictive distribution for an autoregressive model of Bitcoin price, where basically the key aspect of that is the price of Bitcoin today is a simple linear function of the price of Bitcoin yesterday, plus some innovation that has an unknown standard deviation. So I set up my holder for the draws from the prior predictive distribution. In this case, I'm going to generate a sequence of T draws of this autoregressive process, and I want to do that S times so that this prior predicted distribution for Bitcoin prices reflects my uncertainty before I see the data in the parameters mu, phi, and sigma, which are the three that we're dealing with. So we do a loop over S where we draw the expectation of Bitcoin prices unconditional from normal distribution, given our inputs, the location and the scale of that normal distribution. Then we can draw a realization of sigma, which is the standard deviation of the innovations in this process, from an exponential distribution, and scale it up by what our prior expectation of sigma is. Then we can draw a realization of phi from a beta distribution with shape parameters A and B. This is going to be our autoregressive coefficient. And because we're drawing from a beta distribution, it's going to be between 0 and 1. In principle, the autoregressive coefficient could be between -1 and 1. But for most purposes, I think all purposes in the social sciences, it doesn't really make sense to think about negative autoregressive process where, you know, it's sort of, instead of being kind of close to what it was yesterday, it's especially far away from what it was yesterday in the opposite direction. Then we can obtain a realization for Bitcoin prices at time 0, which is the time before the first time that we might observe in our data set. And that is drawn from a normal distribution that doesn't condition on any previous time. You can see in the Lancaster reading that if you derive it, its marginal distribution is like this. We construct the intercept of autoregressive model, which is just mu times 1 minus phi, where different realizations of that come for every S. And now we're ready to make the realization of Bitcoin price at time 1. So that's alpha plus phi times the realization of y at time 0, which we just drew, plus a realization that comes from a normal distribution scaled up by our realization of sigma. That constitutes Bitcoin price at time 1. And then we're able to loop from time 2 all the way up to time capital T, where we just do the same thing, but now we're multiplying by the realization of Bitcoin price at time T minus 1, and we're getting a fresh realization of the errors at every time point. When all that is done, then we can return this matrix of draws from our prior predicted distribution. And so you can see with the Bayesian approach, yes, we're doing S simulations, and S can be sort of whatever big number we want. But the reason why we're doing S simulations of this process is to get a sense of what we think the data will look like before we actually collect it. And what we think the data will look like before we collect it is a function of our uncertainty about what these parameters are. And so our uncertainty about mu is reflected in this normal distribution. Our uncertainty about sigma is reflected in this exponential distribution. Our uncertainty about phi over the 0 to 1 interval is reflected by this beta distribution. And all of that uncertainty is propagated to our uncertainty about what Bitcoin prices are going to be at any particular point in time. So the reason why we do this S times for S is some large number is to really get a complete coverage of our uncertainty about what these parameters could be and how that propagates to our uncertainty about what the data might look like. Becca.
Can you separate, like, you may have more certainty about, this is a little bit theoretical, but like, you may have more certainty about what the data will look like, but you also think that it will be very variable, but you have certainty about that.
Yes, so you're certain it's variable.
Right.
Yes.
Is that, like, how, this only has, like, sigma as one measure of, like, how variable you think it is, but how? Right.
And so if you thought this was an extremely noisy process, like Bitcoin has a tendency to be, then you would want to select your input to this whole thing, your expectation of sigma, to be some large number. And that, so the innovations, the error in this process from, you know, today to tomorrow can be like really big, really small, and or really big positive, really big negative, or really small. And so you would see if you did that, the price of simulated Bitcoins would jump around a lot from one day to the next. But you could also, in addition, express something like that. How close is phi to 1? If phi is really close to 0, then it's just going to kind of look like white noise. And that is probably not what you would anticipate. But if phi is really close to 1, it's going to look closer to a random walk, which you might have some theoretical model from finance to suggest, at least in the aggregate, that stock prices are well modeled by a random walk. So people always, if they're willing to collect data and analyze it, are always going to have some beliefs or intuitions as to what things are going to look like. What you have to do, and why this is challenging, is learn how to express what you think in terms of probability distributions and in terms of parameters in probability distributions of generated models that are interpretable and have meaning. It was one of the things that Krushke was emphasizing in the reading for Tuesday. It doesn't do you a whole lot of good to specify this generative model if you can't interpret what the parameters are. Because if you can't interpret what the parameters are, how are you supposed to express your prior beliefs about what you think they are before you see the data? Other questions about that? Okay. So now let's see what it would look like if we were doing frequentist simulations. Now the STAN language is sort of a general purpose language for doing statistics and probability, and as such, it can't prevent you from doing frequentist stuff in STAN, unfortunately. So if we wanted to set up a simulation from a frequentist perspective, it would superficially kind of look the same, but actually there's some very important differences here. So one of the important differences is for this function, okay, we're inputting S and T, number of simulations, number of time points, but the other inputs to the function, the arguments, trailing arguments to the function, are all about parameters for our priors that we're going to specify as known. They're exogenous knowns. So, for mu, what is the expectation and the standard deviation of your normal prior for mu, where mu is the unconditional expectation of Bitcoin price? What is your expectation of sigma? What are the shape parameters that go into your beta prior for phi? And so the Bayesian, the priors and whatnot are conditional on these values that you input that express your beliefs about the parameters. From a frequentist perspective, remember, everything that they're doing is conditional on the parameters. You just put in as arguments to your function mu, phi, and sigma. And you can put in whatever values you want, as long as like sigma is positive and phi is between -1 and 1. But you just put them in. You take your function is taking them as given and then evaluating the implications of that. So here we're going to allocate a vector of size S. This is going to hold our OLS estimates of phi across S different realizations of this autoregressive data generating process. So the function we're interested, our G function here, is the OLS estimator of phi across realizations of this data generating process of size T. So because mu and sigma are just inputs to this function, we can calculate alpha only once because mu and phi are not changing. Okay, we got a little of this stuff. Now we're looping over S. We get a realization of the price at time 0. Also, where'd tau come from? Oh, here's tau. Another thing that does not change from one S to the next. Then we're going to allocate ourselves a vector of length t called y. The first one is going to take a realization conditional on our realization of y naught. And this expression here is the same as the Bayesian one for time 1. That one there. The difference being, for the frequentist, the parameters mu, phi, and sigma are inputs to this function, whereas for the Bayesian, things about your prior inputs to your prior distributions are coming in as arguments to the function. So then we loop from 2 to t, pretty much the same, or exactly the same as a Bayesian would do, conditional on alpha and phi and sigma and all that. So after we've accumulated t, capital T realizations of this, we can make a subvector that is just the first t minus 1 and the first t minus 1, that's going to be what I call y lag, and the last t minus 1, that's what I would call y temp. And then the OLS estimator for this coefficient can just be written as the sum of the element-wise product between y and its lag divided by the sum of the squares for the lag of y. And so this is the same as the OLS expression in the bivariate case if you consider y lag to be your predictor. So ordinarily this might be called like x. So the sum between y and x divided by the sum of squares x. That is the equation for OLS in the bivariate case where there's no control variables or anything like that. I should point out that the dot star operator in Stan indicates element-wise multiplication of two vectors. Anyway, this is the OLS estimate of what phi is. And we do that s times, and then we can return that collection of OLS estimates out at the end. And so one of the reasons why frequentist approach got a head start on the Bayesian approach is they were in a lot of cases able to analyze, well, what is the distribution of this thing going to be analytically? Because they didn't have computers to do the simulations. But I think the analytical derivations, if you don't have a whole lot of experience with that, really just obfuscate what it is that they're trying to demonstrate, and that it's more clear to demonstrate these with simulations. Okay, so it's pretty clear that mu and phi and sigma just drop out of nowhere, and everything inside this function is conditional on those parameters. Okay, we'll just sort of let that slide for now. We're generating data or simulations of data according to this autoregressive process, which is the same as what Bayesians would do, but the main difference between the Bayesian approach and the frequentist approach in these simulations is we're also drawing mu and sigma and phi from distributions that reflect our beliefs about those, whereas here they're just coming in as fixed constants. And so what frequentists are interested in doing is evaluating this so-called sampling distribution of some function, like the OLS estimator, across repeated samples of size t from this data generating process. And then, you know, what are the properties of that distribution, which is not a posterior distribution. So this does not yield a posterior distribution either. We're not quite ready to do that. We'll start doing that next week when we get into MC. So there's no observed data coming in here. This is just what we think the data is going to look like before we collect it. But anyway, here we actually are conducting a frequentist estimator, OLS. It's the same as maximum likelihood in this case, and we're analyzing the properties of this frequentist estimator over repeated samples, S of them in particular, where S is some large number. Okay, so we can do exposed Stan functions of frequentist RNG.stan. We can just choose some values, like phi is 3/4, mu is 0, sigma is 1. We can do 10,000 realizations of this process. where this process means autoregressive for t periods. And we're going to pretty much instantly get those simulations back. We can plot a histogram of our OLS estimates for phi, and they look a little bit like this. So the red line is the true value of phi, which is right here, 0.75. But if you look at this, occasionally you get estimates of phi that are higher than 1, which means it would be an explosive process, and probably the Earth would have exploded already if that were true. Sometimes you get realizations of phi hat that are negative, even though the true phi is positive, but the data are random. And so if there's a positive probability of something, it's going to happen if you do enough simulations. Those are rare, but it's not entirely uncommon to get an estimate of phi that's around 0.5 or something like that. And there's more underestimation of phi happening here than there is overestimation of phi. And so in that situation, we say the OLS estimator of phi is biased because the true phi is not equal to the expectation of the estimator. And theoretically, the estimation of the estimator is this integral, 30-dimensional integral of our OLS estimation function. So this is our G function here, multiplied by the PDF of the data, product from t equal 2 to t. So the assumption of this autoregressive process is that conditional on last period and phi and mu and all that, the observations are conditionally independent of each other. And so the probability distribution for all t observations can be written as the product of, well, t minus 1 PDF evaluations for each of the t periods. So this is the G function. This is the joint distribution of all t periods, joint distribution of the data over all t periods. But because the observations are conditionally independent of each other, we can use the multiplication rule, and we don't have to worry about the conditioning. And basically, the conditioning is all taken care of for us here. And the joint distribution is just the product of the 29 individual contributions, and we integrate that over the data space. Of course, that looks like a really hard 30-dimensional integral to do, and so it's way easier to just do like 10,000 simulations and take the mean of those, because the Monte Carlo estimator of this expectation, weak law of large numbers, is going to converge to the true expectation. And the true expectation is a little bit less than the actual phi that we put in. So phi here is 0.75. The average of phi hat, I think, is about 0.7. So the OLS estimator for an autoregressive model is a little bit biased towards 0. So a lot is, I guess, made of the fact that frequentist estimators can sometimes be unbiased on their own terms. And unbiased versus biased is a really loaded phrase. So you say, you're biased or something like that. You think like, well, Fox News is biased. In the sense it's sort of like selectively reporting the information or not really telling the truth. When we talk about bias of an estimator, there's no like moral connotations to it. It means this like integral is not equal to the thing that you're estimating, this integral over the data. So some frequentist estimators are unbiased, meaning their expectation with a finite sample is equal, the expectation of the estimator with a finite sample is equal to the thing that it estimates. Sample means, OLS coefficients where the predictors are not lags of the outcome. A couple other things. You can actually construct an unbiased estimator over different realizations of the sample from the data generating process. But a lot of frequentist estimators are actually biased in finite samples. And if that is the case, frequentists will usually point out that they are nevertheless consistent. So the bias and the variance both get smaller as you get more and more observations. So as t gets bigger and bigger. And this is something that a lot of people, when they're first learning applied statistics, are really frustrated with, and then they just kind of come to accept it. Except for Bayesians, who like it always gets them like really bothered by. It's saying, okay, well, here we have a biased estimator a little bit. That sounds kind of bad. And then frequentists say, well, if you just had more data, it would be better. But if it was feasible for me to get more data, like without having to pay a whole lot of money, I would have already done it. So we're talking about a hypothetical that is, you know, not going to transpire. Moreover, this whole distribution thing is, you know, what if we ran this 10,000 times? On average, it's not that bad. But in reality, this is not going to get done 10,000 times. We're going to do it once and then see where it goes from there. Maybe somebody else tries to replicate it, you know, once. So maybe a couple times this gets done. We're not going to be averaging over 10,000 attempts here. We're essentially going to get one shot. You get, you know, one slice of this histogram. Could be too low, could be too high. On average, it's not bad, but nobody's actually averaging. So that's also kind of a moot point. Rashika, you want to jump in?
Isn't it the case that the estimate is biased between variance trade-off? So it is biased, we need to reduce the variance of
that is a true statement. So a lot of frequentist estimators, so there's always like multiple frequentist estimators for the same population parameter. A number of them are biased, which is to say the expectation of the estimator is not equal to the thing that it's estimating in a finite sample. But the expectation of the difference between the thing you're estimating and your point estimate squared, that's the variance of the estimator, that can be big or small. And so when comparing two frequentist estimators, one may have a higher bias, but a lower variance, and another may have like a little less bias, but more variance. And you have to have like some way of saying which one is better. A long time ago, they were more frequentists were more of the persuasion that you seek the estimator that has the lowest variance among estimators that have zero bias. So minimize the variance subject to the constraint that bias is zero. That only left them with like 4 estimators. So they had to change their standards. And today it's more common to see frequentists refer to the mean squared error, which is the square of the bias plus the variance. So it takes both of those into account. Some of those two things, mean squared error, and a lot of people prefer estimators that have a low mean squared error, even if the bias is non-zero. If mean squared error is the criterion you're interested in across samples of size t from this data generating process, yeah, sure. Believe.
I'm still not sure about the question I asked before, in the sense of when I think about how frequentists work, I don't have this feeling that there's this first step where you kind of just select certain parameters. Like here, the size of phi, like mu and sigma, for instance. So I was just wondering if you could give like a more concrete example where this happens. Like I still don't. I get the steps in the simulation. I don't get it, like what happens in real life.
Right. So in real life, you're not given phi or mu or sigma. You get data, let's say 30 observations. That'd be typical in political science for annual data. And you say, okay, I'm going to estimate this thing with OLS or maximum likelihood or whatever. And so you get one phi hat. You don't know how close that phi hat really is to the true phi. But you know that you went through a process that on average is not so bad. Like the bias is kind of small. So you could be way out here with your one realization. You could be way up here with your one realization, but you followed a rule. And people who follow that rule all the time will, on average, land on their feet.
So then I'm just like, so now we are conditioning on something like in the
Yeah.
which we can't see.
Yes.
Or which we don't like, which we don't know.
Correct.
But so how's the conditioning happening? So what do we use to condition?
Because we just stuck in, like nature, stuck in essentially arbitrary values of mu, phi, and sigma into this thing, ran it for s equal 1, gave the data to you, and you did OLS one time. So this is a very convoluted way for you to get one draw from whatever distribution that is. And you're okay, I've got one draw.
I just didn't understand that the first part is happening in the function, what nature.
Yes.
You were saying that it's like
right. And what we can prove analytically, although it's easier to show with simulations, if nature were to do this over and over again and give 30 realizations of this process to you and 9,999 of your closest friends, and you all did OLS, average your results at the end, it'd be not bad. But I assume 9,999 of your closest friends are not doing, OLS in their free time. Robert.
So if we just have the sample estimates of each of those parameters,
yes.
We're actually doing analysis.
One of them. Yeah.
And those are, sample means unbiased, but we have one. And then,
well, in this case, it's not unbiased. It is biased a little bit. There's more underestimation than there is overestimation.
So like the sample mean.
Yes. So if we didn't do the autoregressive thing, we just estimated the mean. That is an unbiased estimator.
But then we're going to take that.
Dave.
I'm just wondering what's at stake here. I mean, like as a political scientist, when we have an estimate and it's like a little bit lower on the coefficient, I'm looking at that. It doesn't matter to me really if there's like a 0.1 difference.
For a lot of purposes, the bias in this case the bias is small. I think frequentists have a tendency, particularly older frequentists, to get overly excited about small biases because what more people are interested in is the mean squared error. The difficulty here is, you're not guaranteed to get the mean of this distribution in one shot. So it's entirely probable that you could get 0.4 and the real thing is 0.75. And that might actually be politically, or for political science research terms, a big loss. You might get something that's greater than 1 and you say, okay, this makes no sense. And you just give up on the research thing, even though the true value 0.75 is in the sensible region. So yeah, on average, it's not so bad, but you don't get the average, you get 1. And the spread of this from like real bad to kind of bad to real bad on the other side is relevant, particularly considering we don't know which one we are. We just got one random draw. So that's I think in a nutshell the differences about what we're talking about. here. So G is the OLS estimator. We're weighting it by the conditional distribution of the data given the parameters, integrating it over the data, but we're not actually given the parameters. This is like a description of nature. Nature is given the parameters. We're trying to estimate it. But, you know, estimating something with a probability apparatus that conditions on the thing that we're estimating is not the first way that a lot of people would think about going about this. And, you know, in terms of just person on the street talking about the probability who's going to win the Super Bowl, it's, you know, okay, what's the conditional distribution of the thing we don't know, given all the data we've observed on football this season, past seasons. We actually are given that. So it makes more sense to do our conditional distributions conditional on the data rather than conditional on the unknown parameters. Okay, so reading from Lancaster, I really like first chapter. The whole book has several important points. One is the difference between statistics versus econometrics. Lancaster is an econometrician by training. And it sort of says, well, statisticians, they just kind of get the data and they estimate the sample mean, sample variance. Whereas econometricians have this, you know, usually a model of agents who are behaving rationally, but maybe they don't have complete information. And you're trying to get a model of, like, you know, what buyers and sellers and stuff like that are doing. And so I would say that's maybe an overdrawn distinction, or maybe a more accurate distinction is people who are doing quantitative analysis stuff with no particular model of the data generating process in mind, might call that like exploratory data analysis or something, versus people, whether they're economists or not, who have something of a theoretical model for this data generating process that they could simulate from. Of course, if you take the Bayesian perspective, it's not just okay to say, okay, here's our model, it involves mu, phi, sigma, whatever. You also have to say, well, what do you think before you see the data, the distribution of your beliefs about these parameters are. That's part of the model. But, you know, if you can draw from your priors, you can draw from a generative model of the data. Another important point is that choosing your likelihood function is not fundamentally different or like less subjective or anything like that than choosing your prior. From a probability perspective, it's exactly the same thing. Moreover, it's correct to point out that it doesn't really have to be your prior. You can do Bayesian analysis with somebody else's prior, as long as they can express the information you need to know, so you can characterize their beliefs using probability distributions. And that can be like getting blood from a stone sometimes, but in principle, you could do this on behalf of somebody else. Meant to say it before you did the reading, but I'll say it now, that Lancaster parameterizes the normal distribution as expectation mu, and parameter tau, which is said to be the precision. So the precision is defined as the reciprocal of the variance. And that was kind of a convenient way of parameterizing the normal distribution for Bayesians in the 1990s. This book was from like 2002, 2003. It's not really useful today, and it's just sort of confusing to think about what is the reciprocal of the variance. And so in Stan and in R and pretty much a lot of things nowadays that are not bugs, we parameterize the normal distribution with mu and sigma. But obviously, tau and sigma are related in a very easy way. Another point Lancaster makes is that for a lot of purposes, simulated data is more useful, at least more useful for understanding what's going on than data from the wild, which are going to have all kinds of messiness to it, missing values, measurement error, you know, all kinds of stuff. You don't know if the wild data is actually coming from your generative model. So in order to understand what's going on, it's better to simulate from your prior predicted distribution, make graphs and stuff like that, in order to get a better handle on things. Toward the middle, Lancaster talks about the so-called likelihood principle. which, to just be a little hand wavy about it, the principle is that the data which might have been seen but were not are irrelevant to the analysis. Goes on to say that professional opinion is divided about whether inference should adhere to the likelihood principle. However, it's actually Bayesians who adhere to the likelihood principle, and people who use maximum likelihood don't. So for frequentists, data that are not just in your sample, but other data that you could have gotten from the population are actually critical to the whole apparatus of making inferences with standard errors and confidence intervals and p-values and all that, even though you don't actually observe those samples that you didn't take. But this principle seems, intuitive enough, I think, to most people. However, it spawned a long and I think somewhat ridiculous debate where people, this was, like in the 1940s or somewhere around that originally, said, well, here's some other principles, 2 of them, that seem pretty intuitive, and then do like a long convoluted proof that shows if those 2 principles that you think are pretty intuitive, if you accept those, that implies you have to believe the likelihood principle. And because it was a long convoluted proof, there's been like 50 years of debate as to whether the proof is actually correct. But whether it is or whether it isn't, and I think in recent years they've done more to demonstrate that it basically was correct if you just add some additional details to it. But anyway, all it says is if you have these 2 principles that seem pretty intuitive, they imply something that was already intuitive. We didn't really need a 50-year debate about proving whether it's intuitive that data that weren't actually seen shouldn't be relevant to the analysis. But the debate goes on. Lancaster also points out that because Bayesian inference is conditional only on the data that you have, your data don't necessarily have to be a sample from any well-defined population. Your posterior beliefs about theta, etc., strictly speaking, only refer to the data generating process for those observations that you have, might not be generalizable outside of your data set. That requires some additional argumentation that the Bayesian thing, doesn't really speak to. Have a definition of identification, which is a word that people kind of throw around oftentimes without really defining it precisely. Lancaster follows the econometrician tradition of saying a value of a parameter is identified if there is no other value for that parameter such that the PDF of the data given the parameters is the same for those parameters for all values of y in its sample space omega. So this is a pre-data statement. Basically, if there's 2 values of the parameter such that the PDF is going to be the same, irrespective of what y is, then that parameter theta is not identified. And a model is identified if all the parameters in that model are identified. Finally, Lancaster in the appendix lists several important probability distributions that can be used for priors or for likelihoods. And as I was alluding to earlier, people always have some intuitions about what these parameters are, but the difficulty is expressing that in terms of probability distributions. And that's something when people first start out learning how to do Bayesian stuff seems like a very daunting task, because for the most part when they come in, they don't really know that many probability distributions to express their beliefs with. It's sort of like when you would go to IHOP and they would give you like a box of crayons that had 3 crayons in it. And you're like, how am I supposed to do my thing when I only have 3 crayons to choose from? It's sort of the same thing when all you know is like normal, Poisson, and beta. But there's an infinite number of probability distributions out there. There's like hundreds of them on Wikipedia that, probably one of them would be useful enough to describe your beliefs about the parameters or about the data generating process in any particular situation. You just got to find in the like box of crayons that is Wikipedia, which is the one that you need for your artwork. Robert.
I'm not totally sure I understand the simulated data versus wild data. For doing what exactly is he saying the simulated data?
So definitely for doing the last step, which is to get your posterior beliefs about the unknowns given the known data, you have to be using wild data there. In terms of understanding what is going on, making sure your software is working right, making sure your prior distributions make sense, etc. For all the stuff that you would do before you pre-registered your analysis, simulated data is like ideal for that because it's clean. Okay, so moving on to how we might choose a distribution. One principle that some but not all Bayesians favor for a way of choosing a distribution, and this actually applies whether you're talking about a prior distribution or a likelihood, but here I'll write it out for a prior distribution. So we want to choose some prior. So we have this like unknown f function that we want to use as our prior for a parameter theta. And the principle of maximum entropy says choose your prior PDF in order to maximize the entropy, which is the expectation of negative log PDF. So that's your G function. Weight it by your prior PDF, integrate it over theta. That's going to be some number. So that is the entropy. So choose F to maximize the entropy, subject to the restrictions that the PDF integrates to 1, and subject to the restriction that some other G function, its expectation is equal to some known value M, which you specify. And you can specify, multiple restrictions here, 1 or 2 or 3 or whatever. But basically, in order to do this, if you have 3 pieces of information, 3 restrictions here, then you're going to be looking for a probability distribution that has 3 things to the right of its vertical bar. Anyway, so these, or you supply these values in, they constitute your restrictions in this constrained optimization problem. You do this calculus of variation thing to find your unknown function that maximizes the entropy subject to the constraints. And that's how you might choose a probability distribution. Now, the intuition of this is that in the case of a discrete random variable, which theta ordinarily wouldn't be, a uniform distribution reaches the theoretical upper bound of entropy. And that really is sort of a connection with information theory. The distribution that has the most entropy has the least information in it. And the uniform distribution has the least information among all distributions about a parameter, at least in the discrete case. It's a little bit messy in the continuous case, but just by analogy, maximum entropy distribution is the probability distribution that is closest to uniform, but at the same time satisfying the constraints that you give it M, and also that it has to integrate to 1. And so, in other words, the maximum entropy distribution conveys the least amount of extra information about the parameter theta above and beyond the information you already supplied by specifying the values of these expectations of some G function. And so you're sort of choosing a distribution that has the information that you want to convey, but as little as possible extra information. It's sort of like, you invite your friends to the party and they come but bring the fewest amount of their friends who you don't really like. Yes?
Was it kind of like connected to the idea of physical? Kind of like I poured salt into a glass of water and then I would initially assume, no, this totally makes sense, right? So if I stirred the salt in the water, I would assume that there's the same concentration of salt everywhere. that conveys the least amount of information. That's sort of the mean state. If I started to solve thousands of times, I assume that. And then if I poured water on top, then I'm constraining it, then I need to do the right.
If you say so. I mean, there's some deep connections here between like old school information theory and probability theory. I think most of us don't have as acute understanding of salt as you do. So I'm not sure if what you said matches this, but I know that this is a way that people often choose priors, and you could also do it for likelihoods to sort of convey the least amount of unintended information. So the intended information is all these m's, their expectations of g functions that you supply. So you know you want to convey that information. And then as little as possible other information coming along for the ride. If that makes sense in terms of salt. Rishika. Yeah. We'll do one next in a simpler example than the one that we just did. Was there another question over here? Stephanie?
The extra, say like the extra, it's a little extra information you need. Could you just think about that as like data without a lot of noise?
Yeah. So through the prior, you're sort of saying indirectly what you think the data are going to look like. And if your prior is like coming with information that you didn't intend, then that is definitely going to affect your prior predictive distribution for what you think the data would look like. Okay, so what are some examples of this? You don't have to actually do that calculus of variation thing because somebody else has already done it for you. And there's a few important examples. So if theta is some closed set, like the 0 to 1 interval, then the uniform prior is going to be the maximum entropy distribution for that theta. And if it's 0 to 1, the uniform PDF is equal to 1 over 1, which is just 1. So anytime it can be like a sphere or some other stuff like that, anytime you have this like connected set that's bounded, uniform on that set is going to be maximum entropy. It's easiest to think about in the intervals on the real line, but it applies to more general parameter spaces. Second important example, if your parameter space theta is the entire real line and you have two pieces of information, the expectation mu, which you're willing to supply, and the expectation of x squared minus mu squared, whatever the variance. So if you're willing to supply the mean and the variance, and you know that this can be any real number and nothing else, the maximum entropy distribution is the normal distribution with this mean and this standard deviation. A lot of the maximum entropy distributions have only been figured out in the univariate case, but actually this one could be generalized to bivariate and multivariate normal if you, in addition to the mean and the variance, have supplied values of the covariances to go into those multivariate normal distributions. And so this is one justification for the use, perhaps overuse, of the normal distribution in the social sciences or the sciences generally. So you can do this for picking the likelihood, etc. So if you're willing to say the mean of the errors is 0 and it has some variance, then the least informative distribution, the maximum entropy distribution, is the normal. If your sample space is all positive real numbers and you fix the expectation and nothing else, then the maximum entropy distribution is the exponential distribution, which has expectation mu. However, you often see the exponential distribution written in terms of the rate parameter lambda, which is just the reciprocal of mean. Now, kind of unfortunate thing about these maximum entropy distributions is that all these conditions are based on expectations of g functions. Implicitly, that involves doing an integral. And so it can be hard to say like what you think of variance is or what you think of mean is. In the case of the exponential distribution, you can utilize the fact that the median of an exponential distribution is equal to mu log 2. So if you can think about what you think the median is, you just divide that by log 2, and now you're ready to go with a value of mu. Same thing kind of with a normal distribution. So, you know, the mean, median, and mode is all the same, and that is usually reasonable enough to think about. But if you ask somebody, well, what do you think is the variance of this thing? And it's kind of like, I don't really know. And one, because it involves an integral, which is sort of hard to do in your head, but also because it involves an integral that goes out to positive infinity. And those are really influenced by the thickness of the tail, and like little differences can make a big difference to the variance and stuff like that. So let's try to make it something simpler. We know that the normal distribution, 2/3 of it is going to be between plus and minus 1 standard deviation of the mean. So flip it around and say, okay, what would be like, you know, the value of sigma such that I think, you know, 2/3 of that are going to be within plus or minus of the mean. Okay, that tells you sigma, and, you know, now you're ready to go. Other distributions, binomial, Poisson, those are maximum entropy given their respective expectations and their respective discrete sample spaces, provides some justification for using those as our likelihoods. There's a bunch of other examples on Wikipedia. I should point out that the constraints that justify those as maximum entropy distributions are often like weird. It's like, you know, what's your expectation of the derivative of the logarithm of, you know, something? Fix that, and then I'll tell you what the maximum entropy distribution is. And so oftentimes you're going to have to be in a situation where you like flip things around in order to make it more intuitive. So so how does this play out in the case of a beta prior, which we were talking about with the Ebola example and whatnot? So the beta is one of these things that's maximum entropy for a given expected log theta and a given expected log 1 minus theta. And so if I'd asked when we were playing priors, right, like what is your expectation of the logarithm of 1 minus the cure probability? You might have looked at me like, oh, it's crazy. But if your beliefs are such that the expectation of the log theta is equal to the expectation of log 1 minus theta, then that implies the shape parameters are both equal to 1. And the beta distribution in that case is going to simplify to uniform on the 0 to 1 interval, which, as we said before, is always the case on a closed interval. And if the likelihood is binomial, we saw, you know, the posterior is going to be beta with shape parameters A star and B star, which are just bumped up by y and n minus y. And so you can see this uniform maximum entropy prior is basically like adding 1 success and 1 failure beyond what you see in the data. And you may say, okay, well, that seems fine. But to do that denies the possibility that theta is exactly 0 or theta is exactly 1 if you're tacking on 1 of each to the posterior distribution through a beta 1,1 prior. Now, in a lot of situations, you might say, yeah, I know it's not exactly 0 and I know it's not exactly 1. And so that might seem reasonable. However, this guy named Haldane a long time ago took this argument and ran with it, saying, well, the least informative beta prior would be to take the limit as A goes to 0 and B goes to 0, which turns out to be a uniform prior on the log odds, eta. So we have one uniform prior that's maximum entropy for pi, or whatever theta is, the cure probability. And we have another uniform prior for the log odds. And these are different, even though there's a simple, albeit nonlinear transformation between log odds and probability. So this other guy, Harold Jeffreys, argued that the most reasonable way of constructing a prior would be one that conveys the same information, same amount of information about theta as it does about eta. And that turns out to be a beta prior with both shape parameters equal to 0.5, which is this U-shaped thing, which may not correspond to anything that you think is reasonable, about the cure probability of a drug. So you're basically saying, you know, there's a really high chance that the drug kills you. Not merely that you die because you have Ebola, but the Ebola drug kills you before the Ebola does. It's been known to happen with pharmaceuticals, but it's not what we hope happens. Or, you know, just as likely, it, you know, cures you. Like the cure probability could easily be, you know, 0.9. And, you know, it's a very low probability of being around 0.5, which is the probability you survive if you don't get any treatment. So this is a weird thing to think about a drug and a lot of others, this Jeffreys prior, but, you know, it kind of makes sense that you should have the same amount of information about theta as you do about eta. But it doesn't always work out that way. And that's why I put uninformative in quotation marks. All these priors convey some information, and there's no universal agreement as to what constitutes like least informative. It sort of depends on what you mean. So Jeffreys prior more generally, it's proportional to the square root of the Fisher information, which is ironic because Fisher hated Jeffreys among like everyone else. But Jeffreys, you know, if you ask people on the street who was Harold Jeffreys, they probably wouldn't be able to tell you. But, you know, back in the 1930s, there was basically one Bayesian in academia. And he took it upon himself to argue in, you know, journal articles and stuff against Fisher and all the other frequentists. And he did that for like 20 years. So all Bayesians really owe a considerable historical debt to Harold Jeffreys. Anyway, he said, well, we should choose this prior proportional to the square root of the Fisher information. And the Fisher information is defined in a totally Fisher way as the negative of the expectation of the second derivative of the log likelihood function. So you work out that analytical that integral analytically, and you get the Fisher information. And then the Jeffreys prior is going to be proportional to the square root of that. So in the case of a scale parameter, a lot of positive distributions over the positive real numbers tend to have scale parameters in them. It works out that the Jeffreys prior is proportional to 1 over theta. But this other guy, very important Bayesian named Ed James, argued that this was really the only case in which the Jeffreys prior made sense. It basically, it's the non-informative prior that conveys the information that the units of theta don't convey any information. In other words, whether we're talking about something that's, you know, measured in pounds or kilograms, the scale parameter of that, it's going to be 1 over theta either way. And the conversion ratio from pounds to kilograms doesn't tell us anything substantively about, you know, what this parameter is going to be. One last thing, we'll have to pick up more stuff with the priors next week. The Jeffreys prior on a scale parameter is a so-called improper prior, meaning it does not integrate to 1 over the positive real numbers. And in some situations, not usually this one, using an improper prior could imply that your posterior distribution is improper. So your posterior PDF does not integrate to 1, and therefore it's completely useless for Bayesian inference. You cannot come up with anything sensible from improper posterior. However, in other situations, many other situations actually, improper prior still yields a proper posterior distribution, but you kind of have to work it out on a case-by-case basis. So just to be on the safe side, a lot of people recommend to use only proper priors because proper priors always yield proper posteriors. But even if you have a proper posterior distribution, if you use the improper prior, it might preclude some other stuff like doing model comparisons, like what's the posterior probability my model is correct. Those are messed up if you use improper priors. A lot of people, particularly if they're coming from this from a frequentist perspective and are sort of suspicious of the whole idea of priors in general, like to specify improper priors if they were going to do something Bayesian, under the sort of misconception that an improper prior is uninformative. But like I was saying, there's lots of ways to think about uninformativeness, and improper priors are not a good one. Really, they're just saying you have incoherent beliefs, because like the sum cumulative total of your beliefs doesn't even integrate to one. And moreover, you can't come up with a generative model from something that stems from improper prior distributions, because you can't draw from improper distribution. So one way you can think about this is like, what if I tried to draw from a normal distribution with a variance of infinity? You'd get an error message, because if the variance is infinite, then the normal distribution doesn't integrate to one. But people, you know, when they do improper priors, are implicitly saying, well, they think R should just give me some number somehow, even though I did R norm with standard deviation infinity. So improper priors, they can also cause computational problems. And so when we get to use Stan, these are discouraged. You want to use proper priors almost all the time. And we'll talk about more ways next week a little bit for doing that. But certainly the principle of maximum entropy is one that a lot of people, McElreath, Jaynes, etc., really think is a good principle. You should at least know what the maximum entropy distribution is in particular situations. Whether you choose to utilize it or not is up to you, but you should know, what they are. Anyway, okay, that's it for today. I'll post homework due next week, and we'll start to learn about